Hope you enjoyed the little bit of snow this morning. It was kind of nice. Always enjoy spring snow because it doesn't last long. It's kind of fun. My daughter was born on May 14th. And the next day, we brought her home from the hospital in the snow. Which is why we love Chicago, because, I mean, everyone talks about San Diego. Oh, the weather's so beautiful. No, it's so boring. It's the same every single day. Ay, ay, ay. I do. I like the seasons. I wouldn't want it cold all the time, but I do like the seasons. All right, so just a little reminder about the schedule. So including this week, we have 3 more weeks of classes and then finals week. And I did check our final and I forgot to write it down, but it is on, let's see, I think it's on Wednesday. Yeah, Wednesday at 2 p.m. will be the final exam. Wednesday, May 12th at 2 p.m. So that's 3 weeks from tomorrow. So we're on schedule as far as the material goes, so that's great. I'm working on your second exam, get those graded soon. We will probably only have one more problem set, 1 or 2, probably 1, we'll see, on the material that we're covering now. And so basically 6 more classes. Yeah, 2 p.m., that's correct. And it is cumulative. However, it will emphasize the material since the second exam. So this material that we're starting now, essentially. So you can be assured that there will be problems and questions on the material from now to the rest of the semester, end of the semester. And then what you'll find is when you go back and study the material that we covered on the first 2 exams, I won't say it's going to seem easy, but it's going to seem a whole lot more straightforward than it did at the time, because a lot of this has been building up. And we're going to talk, for example, again, about solving systems of linear algebraic equations, which we know how to do from chapter 2. So a lot of this stuff is going to kind of start to come together, and you'll see connections, and you'll see that it's, when you go back and study that material, I hope that you find that it's really not that difficult now in hindsight. So obviously I'm not going to be able to test you on everything that we've covered, all the topics, but all the topics are fair game. So definitely the topics that we're covering in this chapter and in the next chapter, so for the rest of the semester, and then everything else before this is you're responsible for, but obviously it'll be more selective in terms of the exam itself. Same format, 2-hour exam this time. That'll be the only difference. Okay, so we're getting down to the end of the semester, sort of, kind of. I don't know about you guys, but I feel like the first part of the semester seemed to fly by really fast, and then we just kind of hit a wall. And I don't know if that was just me or what, but just seemed like kind of around halfway through the semester, third of the way through the semester, it just seems like all of a sudden time slowed down dramatically, which is fine. It's not a bad thing. And it just seems like things are kind of, maybe it's because we didn't have a spring break. I think it was the yeah, so Amira agrees with me. It is interesting because we don't have a spring break in the fall. So you think, well, why should a spring break, if we don't have a spring break in the spring, why should it be so different? But it's just that academic rhythm. We're just so used to that rhythm in the spring, and it does make a difference. Kind of get an opportunity to get caught up and get, and or hit the pause button, get rejuvenated, so that the sprint to the finish line is more manageable. My daughter-in-law teaches in Massachusetts, in the school system there, elementary school, and they actually have 2 breaks. They have a winter break and a spring break. So during winter break, they all go up to New England and go skiing. And then during spring break, which is this week for her, then they do kind of normal spring breaky sorts of trips. So that's kind of nice. I think we should do that here too. Although I guess we can't complain. We do have a month off at Christmas, don't we? So I suppose we can't complain. All right, done complaining. I'm fine. Okay, so we've been looking at 3 of my favorite ODEs. The first 2 were Matthew's equation, which governed the forced pendulum. And we saw some interesting behaviors, stability behaviors in that. The second one was the forced Duffing equation. And that created all kinds of interesting phenomenon with chaos, with very complicated phase plane solutions, with, we talked about, so phase plane plots, Poincare maps, and bifurcation diagrams, all of which are very useful for seeing how these things behave. The third one is the Saltzman-Lorenz model. You may have heard of the Lorenz model. That's how most people refer to it as. I refer to it as the Saltzman-Lorenz model because it was actually Saltzman who derived the model, the mathematical model itself. Lorenz is the famous one because he came along a year or 2 later with a famous paper which is what I'm going to illustrate to you today. But I always felt bad for Saltzman because it was actually his mathematical model that Lorenz picked up on. So I call it the Saltzman-Lorenz model, but it is the same thing as the famous Lorenz model. So this is an example. It's a very simple system of 3 ordinary differential equations. Doesn't look terribly exciting. It even looks less exciting in some ways than the other 2 equations we dealt with, but it does contain deterministic chaos. And it also has a very interesting history and story behind it. So Edward Lorenz actually was a meteorologist. He was a professor of meteorology at MIT in the early 1960s. So this was, think about the time frame. Remember our history way back at the beginning of the semester. So this is only early 60s. This is only, say, 15 years or so after development of the first digital computer. So these are the very early days of digital computing. So very limited computer technology to work with. And he had this very ambitious task of trying to model the atmosphere. So he was looking at a very specific problem. It's called the Rayleigh-Benard convection problem. It's very, very famous. It's been around for, Rayleigh is from the late 1800s, 1880 or so. And it's been around for many, many years. It's been looked at analytically, experimentally, computationally. It's still a problem that people look at today to test various methods and to try to learn the physics of. So he had a very, very, well, again, Saltzman, they had a very, very simplified model of this very, very complex flow. So, which I'll get to in a second. So you can see those first two bullet points there at the top. This is just, I want to emphasize how different actual real research is from kind of the scientific method-based process that we learn in middle school and high school, which makes it sound like it's just this very methodical kind of march forward. And every day we're just kind of building on what was done before. Each day we know a little bit more than we knew the day before. And that represents progress. In fact, there are many, many examples of this. Einstein is an excellent example of this, but Lorenz was as well. He, didn't revolutionize modern physics in the same way, but it did revolutionize our understanding of nonlinear behavior and what can happen. So there's some serendipity involved, which basically means there were some accidents involved, which is very, very common in actual real research. But normally, the vast majority of when we see something strange and when we see something that seems to happen by chance, that doesn't really make sense, it doesn't fit with what we expect, we often throw it away. We write it off as, well, I guess I made a mistake, or I guess it was just a bad day, or someone must have slammed the door to the lab and that messed all of the data up. But he was very astute. He looked at what was happening, and he endeavored to understand why that might be the case. And there's quite a bit of creativity involved as well. And so when you see these scientists, mathematicians who have made great strides in various fields, there's usually some of these elements in there. A bit of accident, but a very keen sense for, ooh, that's unexpected. That's not what I hoped would happen or thought would happen. Therefore, maybe it's revealing some new physics. This is happening actually right now at this very moment. If you follow high energy physics at all, out at Fermi Lab just outside Chicago, they have been working on doing experiments on muons for some time, and they have some data. Now it's not at the level of certainty that is considered to be sufficient to call it a conclusion yet, but it's getting there. And it looks like they may have either identified the possibility or likelihood of a new particle, or maybe even came up with what may lead to an explanation for dark matter. So it's pretty exciting, and these things don't happen very often. And again, you know, when these things happen, people are looking at their monitors and watching the data come in, and day after day, 24/7, monitoring these experiments, in this case, very large experiments out of Fermi. And you see results that don't fit with what you expect. And that's often the time when you get most excited. It's a little scary, because maybe you just made a big boo-boo. Maybe someone forgot to plug in some cryogenic cooler thingamajig somewhere along the beam line, and all the muons are just falling out on the floor, so to speak. So maybe it's a boo-boo, or maybe it's some actual real new physics. So in this case, it really did represent a sea change in how we think about nonlinear systems. So for many years, many years, people have been looking at linear systems. We understood them very well. We had Poincaré was from the early 1900s. So a lot of these developments were very well known, very well developed by this time. And so then nonlinear, you think, oh, okay, well, that's like the proverbial block sliding down the incline in your high school physics class, right? So if you neglect friction, what happens to the block? It goes down. If you include friction, what happens? Well, it just goes down, but just a little bit slower. So qualitatively, it's the same behavior. Quantitatively, it's a little different, but qualitatively, it's just more of the same. And that was kind of the expectation at this time for nonlinear systems. Was, sure, it's going to change the results a little bit, but qualitatively, how different can it be? It's still, in this case, Rayleigh-Benard convection. It's still a spring mass system. So you make the spring nonlinear. Well, how different can it be? Well, turns out it can be quite different. And this is really, again, the sea change that I'm talking about. So let me briefly describe the problem. It's a very simple problem. You have two infinite flat plates. They're parallel to one another. And the bottom one is heated. And then there's a fluid in between. So just say air. So that's the atmosphere. You have the Earth and the upper atmosphere. The Earth's surface is warmer than the upper atmosphere. And so you get convection rolls. So the heated fluid rises and the cooled fluid falls. So you get these convection rolls, and they usually just kind of go on forever. So this is a very simple model of that problem. Here's what it is. So this is the Saltzman-Lorenz model. I won't go through the derivation, but it starts with the full Navier-Stokes equations that you learn about in fluid mechanics, and the energy equation for heat transfer because of the temperature effects. And when you go through the simplification process, which I'll just kind of leave to the side, you end up with three coupled nonlinear first order ODEs. And you say, well, if you know at all what the Navier-Stokes equations look like, which I showed you some time ago, well, a few classes ago, you say, well, wow, that's a lot simpler than Navier-Stokes. So yeah, these are some pretty serious, significant approximations. But in any case, this is what you get. The parameters are sigma, that's the Prandtl number of the fluid, so that's a property of the fluid that has to do with its heat transfer aspects. B is the aspect ratio or the shape of the convection rolls. So are they narrow, tall convection rolls, or are they wide convection rolls? So that's B. And then R is the Rayleigh number, and that is a non-dimensional temperature difference between the two surfaces. So what we're going to do is keep sigma and B the same. So the same fluid, the same convection roll shapes. And we're just going to change the Rayleigh number R. So basically, we're just going to increase the temperature difference between the two surfaces. The governing equations look like this. The dependent variables are X, Y, and Z. They represent the velocity and aspects of the velocity and aspects of the temperature distribution between the two plates. So X, Y, and Z are the flow and the temperature. If you look at the equations, the first equation says dx dt is sigma y minus sigma x. Okay, so that's linear because I just have x alone and y alone. So that's linear. The second equation, dy dt, is rx minus y. Those are linear terms. But then I have an x times a z term. That's nonlinear. X times z, so that's nonlinear. The third equation, dz dt, is x times y. That's nonlinear, minus bz. All right, so these two terms in red, make our system nonlinear. And again, if you just look at this and you say, well, I kind of know what to expect from linear equations. I either get exponential rise, I get exponential decay, I might get oscillations, I might just get steady state behavior. All right, well, I add in these two nonlinear terms. How much different can it really be? Well, let's just see. So let's start with sigma's 3 and B is 1. We're going to keep those the same. So I'm not going to change, again, the fluid, which determines the sigma, and the aspect ratio of the cells, the convection cells, so that's the B. So we're just going to focus on R. We're going to start with R of 10, so that represents a relatively modest temperature difference, and then we'll see what happens as we increase R. All right, initial condition. So at t is equal to 0, we're going to start with x is equal to 6, y is equal to 6, z is equal to 6. Apparently, I felt a bit devilish when I chose the initial conditions. Turns out these are not significant in any way. I was just feeling a little feisty, so I picked 666, the mark of the beast. Okay, so we solve it. R is equal to 10. At t is equal to 0, this is t, going from left to right. They all start at 6, 6, and 6. And then these are u, v, and, sorry, x, y, x, y, and this one is z. And you can see as time progresses, all three are settling down to either 3 for x and y, or 9 for z. And you say, well, that's kind of disappointing because that's pretty linear looking, right? It looks like a damped oscillation that you would get, for example, from the force stuffing equation when you have damping. All right, so that's pretty linear looking for R is equal to 10. Get a damped oscillation, nothing terribly exciting. Let's look at, first of all, in the phase space. So this is a plot now, 3 dimensions, x, y versus z. So here is the initial condition, 666. Ooh. And then it spirals in. That's their trajectory in the phase plane until it gets to this point in the center, which corresponds to x is equal to 3, y is equal to 3, and z is equal to 9. So that's the stationary point. That's the steady solution. So you let this thing go long enough, and wherever it starts, 666 in this case, but wherever it starts, it ends up going to 339. And then it just stays there forever. So it's a steady solution. It's a time invariant solution. Again, rather boring. Let's see what happens when we increase R27. I need to take out these section labels because it takes away from the suspense. So now I'm just going to increase the Rayleigh number, so increase the temperature difference between the two plates. So I expect to get more vigorous convection cells. The velocity should be higher, the temperature difference should be larger, and indeed that's the case. So here are the same 666, that's where they start, and then X and Y, you can see now have a little different behavior. We'll talk about what that means in a moment. And then the Z has also a little different behavior. You'll notice the first thing you notice is that they're not settling down at all. So this is a time of 30, which is when I stop the numerical solution. Up to a time of 30, you don't see any indication that this is settling down to a steady state. You know, the 339 kind of solution that we had before. That's the first thing you notice. The second thing you notice is particularly in the X and Y, you'll notice that they're both negative here for a while, oscillating back and forth, and then they both jump and become positive, and they go back to being negative for a little bit, then they jump to positive, back to negative, positive, negative, positive, negative. And you say, well, what's going on there? Well, that's where the phase plane plot, the XYZ plot, is helpful. So we start out again at 666, same initial condition, but now the trajectory takes us back and forth between these two lobes in an apparently random fashion. Now, the first thing you'll notice is that may look familiar. If you read, if you look at all at this kind of stuff, and you've seen an image of the Lorenz Attractor, even in the popular literature, sometimes you'll see these. That is the Lorenz Attractor. And so again, it might look familiar to you. Basically, there's two lobes. We'll affectionately call them the left and the right lobe. And the lobes represent different sign rotation of the convection cells. So when you're in the left lobe, let's say you're going clockwise, like this. When you're in the right lobe, it's going counterclockwise. So it's the same convection cell, it just abruptly switches directions. It's happily going counterclockwise, and then boom, it switches to clockwise. And you can see here how, like in this case, there's 1, 2, 3, 4, 5. So it goes, in one lobe, the left lobe, say 5 times roughly. Then it does 1 in the right lobe, then 3 in the left, and then 4 in the right, and that and on and on and on. So it's just kind of randomly switching its rotation direction, which seems a little strange. You'd think, well, once it gets going one direction, just keep going, right? It can go faster if it wants, but why would it all of a sudden switch directions? Well, that's what the solution is saying. And clearly, it's not zeroing in on a particular steady or stationary solution. So this is what's called the Lorenz Attractor, and it is a strange attractor. Not all attractors are strange. So let me describe what an attractor is first, and then I'll describe what a strange attractor is. What makes it strange? So an attractor is any region within the phase plane where the solution tends to get attracted to. It's just exactly what it sounds like. So there's a basin of attraction. So there's like a bowl. And as long as you start your initial conditions somewhere in that basin of attraction, in that bowl, it will eventually, usually in a short period of time, as you see here, zero in on this attractor. So this region within the phase plane, in this case, it looks like the butterfly wings, right? So whether I start at 666 or 10, 10, 10, or 1 minus 3, 7, doesn't matter. Eventually, it's going to end up in this same attractor. So that's what an attractor is. Now, what makes it strange is when it has a geometrically complicated shape. So we've seen periodic behavior. Okay, I showed you with the force stuffing equation. If you just have an oscillator going back and forth, you get a circle, you get a periodic solution in the phase plane. So that's a limit cycle. So that's an attractor. Now, it's not strange because it has a very simple shape. As we progressed, as we increased forcing and added in other physics, we got increasingly complicated behaviors or trajectories within the phase plane. So those make it strange. And strange implies, or actually means, that there is chaos. Now, I've said this before, but let me make it even more clear now. So we normally call it chaos, but chaos implies randomness. Chaos implies just sort of whatever complexity, just ended up being this way. And we'll talk about sensitivity to initial conditions in a few minutes. So there's all these elements in chaos, but the real term, what we should really call it, is deterministic chaos. So we say chaos for short, but what we really mean is deterministic chaos. And what deterministic means is we know the governing equations. The governing equations have this behavior in them. It's not just random fluctuations. It's not someone banging the door on the laboratory wall, or when I'm doing the calculations on my computer, I start jumping up and down, and the chip in my computer gets excited and starts making wrong calculations. That's not what this is. This is deterministic. So if you put in the same initial conditions, same equations, you'll get the same solution every time, just like you normally would. So it's not randomness in the way we think about it. It looks random, it looks chaotic, but it is actually very much deterministic. So again, the two lobes correspond to the clockwise and counterclockwise rotation, and you can see how they're switching back and forth in a seemingly random fashion. So apparently it's random, but it's really not. Again, if I do the same calculation again, I'll get the same result with the same initial conditions. Okay, let's look at sensitivity to initial conditions. This is a property of deterministic chaos, of strange attractors, which is very interesting, very telling in terms of what it means for nonlinear systems, and in particular, the Lorenz problem. So sensitivity to initial conditions, it's exactly what it sounds like. This is where the serendipity came in. So what happened was, Lorenz, oh, I should have brought my fan fold paper. So in the good old days, we had these printers that you put the paper in. They had little holes in the edge, and it would kind of have this little spool with the spokes on them, pull the paper through. It made this great sound as it printed on the paper. And, you know, we didn't have nice graphics monitors. I shouldn't say we, I wasn't born yet. Ed didn't have nice graphics monitors to track the solution. He didn't have MATLAB plots, Python plots. So you can just think and imagine he had this fan fold paper, and then 3 columns, X, Y, and Z. And each row was at successive times. So starting off at t is equal to 0, what's the initial conditions for X, Y, and Z? So 6, 6, 6. And then one time step later, what's the X, Y, and Z? Next time, X, Y, and Z. So he had done one of these calculations, which again, at the time, I mean, now it's just, I hit the go button, the results come up immediately on my laptop. But in those days, these were rather heroic kinds of calculations. They were not trivial calculations by any stretch of the imagination. So one day he had done a solution. So he had his X, Y, and Z values. And then he came in the next day and he wanted to continue that solution for a longer period of time. Rather than starting back at 0 again with 6, 6, 6, he decided, well, let me save some time and let me put in some values of X, Y, and Z from the previous day's calculation. I'll put those in as initial conditions. And so he did. He just picked a line and he said, okay, what's the value of X? What's the value of Y? What's the value of Z? Let me put those in as initial conditions. And from then on, for later times, I should get the same values of X, Y, and Z as I did before the previous day, and then I can let it run longer and as long as I'm interested in doing. But here was the problem. The actual calculations on the computer were being done with 6 decimal places of accuracy, six significant figures of accuracy. So, for example, if one of the values was 0.753441, that's what the computer had in its memory, what it was calculating. However, when he was printing out the values on his paper, he only printed out 3 decimal places of accuracy. And in a linear world, based on linear thinking, subject to our experience with linear equations, that seems perfectly fine. If I put in 0.753, because that's what it says in my paper, even though the computer says it's 0.753441, it shouldn't make any difference, right? Fine. Put in the values, those 3 values, put in the 3 significant figures, but they're off by a little bit, seemingly inconsequential. However, after some period of time, so if you compare the 2 results, the X, Y, and Z values track very nicely for some period of time, but you keep going, and all of a sudden, you see that the new X, Y, Z values are very different than the corresponding times of X, Y, Z values from the previous run, which makes no sense. They should be the same. There's no reason why they should diverge by much. You know, tiny little bits, round off errors here and there, but not fundamentally different, or what we would say qualitatively different behavior. But that's exactly what he saw. So what most people would do would say, oh, well, I guess I can't start my runs with intermediate values. I have to always start back at t is equal to 0 and just sit and wait and be patient and then not think anything of it. But he wasn't, he didn't let it die, so to speak. So he looked into it, he did some more tests, saw this behavior over and over again, and started to understand what the reason for this behavior was. So this is the sensitivity to the initial condition. One run had this at a certain time. One run, the other run had this. So a slightly different value. And it turned out that the solution was sensitive to those values, the small difference in those values. So to illustrate that, let's take a look at t is equal to 30. So at the end of the calculation that I showed you before, let's just print out the values of X, Y, and Z. Don't worry about the numbers. Just remember that it's negative, negative, positive. So that means it's in the left lobe. Okay, so X and Y are negative, so it's in the left lobe, which means it's going clockwise or counterclockwise. And let's do this exact same calculation. Everything's exactly the same. The only difference is, rather than at t is equal to 0, z being exactly 6, we're going to say z is 5.999. So obviously the difference is only 0.001. So it's a very small difference. Don't expect to see any fundamentally different behavior. The numbers will be slightly different, but it should track the same trajectory as it goes between the 2 lobes. Well, here's what you get. And you say, well, that looks exactly like what we had before, right? Yeah, it's the same attractor. But let's look at which lobe it's in. In the first case, it was in the left lobe. So if you can find it, I don't know where it is here, someplace, but if you can find, oh, actually it's over in the right lobe, sorry. So right here it is, that's at t is equal to 30, it's in the right lobe. At t is equal to 30. Now, with the small change in one of the initial conditions, if you look at the final values of X, Y, and Z, you'll notice that it is positive, 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 and that should correspond to the left lobe. And I don't know where it is here. Should be somewhere in the left lobe. Can't find it. Oh, you know why? I wasn't supposed to zoom in on this. I was lazy. I put the same plots because I knew they looked the same. On this scale, I knew they looked the same. So I literally used the same plot. I didn't actually print out. I didn't actually print out, oh, Castle, you're terrible. So I did not actually print out the correct plot because I knew that on this scale, the attractor would look the same. But yeah, you're right. So it turns out, oh, sneaky little devil. Well, I did start out with 666, so I guess it is my fault. But anyway, you can see from the values themselves, it's plus, plus, plus. So what does that mean? 2 points that started out right next to each other. So 5.999 and 6, 2 points that start out right next to each other, and they go around this trajectory, within this attractor together for quite some time. But at some point, they start to diverge, such that by t is equal to 30, they're actually in opposite lobes of the attractor. So one of those points is now going clockwise, whereas the other one's going counterclockwise. Completely different qualitative behavior. The block is going up the incline rather than down in a strange sense. All right, so that's sensitivity to initial conditions. Small changes lead to dramatic differences at later times in the behavior of the system. I guess I should change that plot. Ha! This is colloquially or popularly called the butterfly effect. In fact, there was a movie some years ago with that name. And the idea behind that name is that a butterfly someplace, say flapping its wings in India, could eventually, a few weeks later, be the difference between a bright sunny day in Chicago or a raging blizzard. Now, it's a bit of an overstatement because you think, well, yeah, I get the idea, sensitivity to initial conditions. So if the butterfly flaps its wings here or here, that's a slightly different initial condition. And by the time the atmosphere evolves and gets to Chicago, I can see that it's going to be different. But, the bus driving by is going to have more of an effect than the butterfly. I get all that. So it is kind of an overstatement in that sense. But that's what the sensitivity to initial conditions tells you, is that small itty bitty little changes anywhere in the system can lead to dramatic changes, qualitatively different behavior in the behaviors of the system later in time. Completely different. It's going one way rather than the other. So in the context of weather prediction, Lorenz actually recognized, and there's a quote in my book, I have beginning of chapter quotes, and I have for the chapter that covers this material, a quote from his paper that basically is very depressing. It basically says that weather prediction, long-term weather prediction, is not possible. So that was a statement made in 1963. Okay, so now we're in 2021, and if you ask yourself, is long-term weather prediction possible? He was right. The answer is no. Now, if you trust the Farmer's Almanac, of course, that's a different story, but that's not based on science. That's not based on deterministic equations. So, is it true? The answer is yes. So, is weather prediction better today than it was in 1963? Sure. So when I was growing up in the 1970s and 80s, I remember very distinctly 5-day forecasts. So on the news, they would give us a 5-day forecast. We all knew that at best, maybe the first 3 of those 5 days is going to be reasonably accurate. Now, it's not uncommon to get 10-day forecasts. So you say, has it improved? The answer is yes. Because the methods, the algorithms, the science, as well as the computers on which we solve these simulations are much, much more powerful and much, much more accurate, but there's only so much you can do. So those 10-day, I don't know about you, but those 10-day forecasts, I never look beyond 5 days. because you, especially in Chicago, you know it's going to change. If you watched for today's forecast for the last week, it pretty much oscillated every day. So a week ago, they were saying snow today. And then almost every day it was no snow, snow, no snow, snow. And of course, then it did actually snow here, but not at home in the western suburbs. So in my home in the western suburbs. So, and the reason for that is because of the butterfly effect. No matter how accurate your simulations are, so you don't have to stop at 6. Now it's common to use double precision, which is 16 significant figures of accuracy. The models are much, much more accurate. The computers are much bigger and much faster. But again, it's just, there's only so much we can expect out of these models. So that is the butterfly effect, or the sensitivity to initial conditions. So there's 3 things that I've highlighted here, and they're all demonstrated in the Saltzman-Lorenz model. You'll see this in other systems, nonlinear systems as well. They are present in the forced Duffing equation that I showed you last time as well. So the 3 things are, you can get very different qualitative behavior, not just quantitative, not just the numbers are off by 5% or 10%, but the flow's going this way instead of this way. The convection rolls are going clockwise rather than counterclockwise. So you can get very different qualitative behavior depending on the input parameters. That is not the case for linear systems. A linear system is, you put in a certain amount of input and you get a certain amount of output. If I double the input, then I double the output. It's just giving me more of the same, but I don't expect to see fundamentally different behavior from a linear system. Nonlinear system, that's a different story. Second thing you'll notice is the seemingly, again, emphasizing seemingly or apparently random behavior. It's not random. It's coming out of the equations themselves, but it appears random, but it exhibits some underlying order. And that's, again, what we call deterministic chaos. Sensitivity to initial condition, again, is the 3rd one that we see. That's the butterfly effect. Now, let me show you another very interesting property of the Saltzman-Lorenz model that's common to many of these nonlinear systems. They're called periodic orbits. So an orbit, just like in space or satellites, the planets are orbiting the sun, satellites are orbiting the Earth, or wherever you put them in the solar system. So you have these orbits, which means the flow, in this case, the flow is coming back on itself over and over again, periodically. So it's an orbit, it's a shape within the phase plane that is repeating over and over and over again. And you say, well, okay, maybe for r is equal to 10, the boring case, the linear type case, but certainly not for r is equal to 27, certainly not the chaotic case. Don't try to convince me that there's periodic orbits, that there's these shapes within the trajectories within the phase plane that just repeat over and over and over again indefinitely. That can't be true, right? Turns out it is. So these were found by Viswanath in 2003. So let me define a periodic orbit more carefully. So it's a trajectory in the phase plane that repeats itself over and over again. So that's the periodic nature of it. So what that means mathematically is, if I know the period, capital P, then u at t plus p is the same as u at t. So every p time, it's exactly back to the same spot it was 1 p ago, and 2 p's ago, and 3 p's ago, and 47,000 p's ago. So that's it's just coming back on itself. So that's the periodic nature. So in the Saltzman-Lorenz model, the way we'll define the periodic orbits is, when it's in one lobe, we'll call it A. We'll say it's in the A lobe. When it's in the other lobe, we'll call it B. And then you have sequences of A's and B's. So A, B would mean it goes around the one lobe once, the A lobe once, and then the B lobe, and then it comes back to the A, B, A, B, A, B, A, B over and over again. If it's A, B, A, B, sorry, so if it's A, A, B, A, A, B, then it does 2 around A, 1 around B, 2 around A, 1 around B. Okay, so the way we're going to do this is with those definitions for the A and B lobes, we're going to fix the value of Z at t is equal to be 0 to be 27. It's completely arbitrary. And then we're going to choose the X and Y values that put us on the periodic orbit. For that particular value of Z, for the orbit we want, AB, AAB, or whichever orbit we want, we're going to start with Z is equal to 27 and calculate the value of X and Y that puts us on the orbit. He used different values for sigma, B, and R. So 10, 8/3, and 28. Not terribly significant, but he just so happened to use different values. So here is, I'll show you 3 examples. Here's the AB orbit. So here's the AB orbit. So it goes around one lobe once, then the other lobe, A, B, forever. So Z is 27, and you calculate in order to be on this particular trajectory, X at t is equal to 0 is minus 13.76 ... Y at t is equal to 0 is minus 19.57 ... And that gives you, puts you on this orbit that has a period of 1.559. You can calculate that all from the equations. And it literally just goes back, keeps going back on itself over and over again. So it's a closed periodic orbit, and it just goes back on itself. So it's periodic over and over again. Now this is in the chaotic regime. Okay, so this is when you're getting this weird behavior where it's flip-flopping randomly back and forth. There's this one AB orbit that's there all the time. There's also an AAB orbit. So 2 times around, in this case, the left lobe, then the B, A, B, A, B. And you can calculate again where you have to start to be on that orbit. And it will just go forever and ever and ever and stay on that orbit with a particular period. Here's a AABBB orbit. So 2 times around A, 3 times around B, then twice around A, B, over and over again. Here's the initial conditions that put you on that orbit with this period. How many of these are there? Well, turns out there's an infinity of them. And that's a property of chaotic systems, deterministic chaos. You have an infinity of these periodic orbits. But once again, the point is there's this underlying structure, very predictable structure within this seemingly complicated flow. So all infinity of these orbits are contained within these chaotic solutions. Now, he didn't calculate all infinity of them. He actually calculated the first 111,011. And that corresponds to symbols of up to 20. So every possible A-B combination up to 20 symbols he did. How many are there? There's still an infinity of more. So he did a lot, 111,011. There's still an infinity more that he hadn't done. But anyway, the point is that is another property of these chaotic systems. He also found that in turbulent Couette flow, which is an actual real flow, full Navier-Stokes equations, PDEs rather than 3 simple looking ODEs, Saltzman-Lorenz model. If you look at the full PDE, turbulent fluid flow Navier-Stokes, it turns out that there are also an infinity of orbits contained within those solutions. So this is, again, this is a property of deterministic chaos, this infinite number of periodic solutions. Now, the fact, this is extremely unusual, the fact that in a system of 3 nonlinear ODEs and in a system of PDEs that are also nonlinear, that you would have the same very similar behavior in terms of the periodic orbits is very unexpected. And again, it turns out it's a property of these chaotic systems. This stuff is a lot of fun. It's very fascinating. This is just my three favorite, I have more. I picked three because that's how many kids I have, right? So my three favorite kids are my three kids. So my three favorite ODEs, there's more than three, but these are my three favorite. And again, as I've said before, I've limited myself to ODs. I haven't even talked about PDs. I've mentioned the Quet flow, which is based on PDs. But so if you want to learn more, this is called dynamical systems theory. And these different ways of understanding and quantifying and understanding, I just said that, but you really want to understand it. So understand these kinds of solutions is called dynamical systems theory, which basically just means how do we characterize behavior of time-dependent systems. They're dynamic in the sense that they're changing with time. So if you're interested in more on that, that's chapter 5 in the Matrix Methods book. If you're interested in more on that. Fascinating, endless, lots of fun. So if you like differential equations, but you want to look at differential equations from a more physical, more scientific, more engineering viewpoint, then take a look at that chapter, and it's fascinating. You'll have a whole different appreciation for differential equations and the kinds of behaviors that they can exhibit. All right, any questions about those three examples? Okay, so what I want to do for the rest of our class today is just look at a couple general considerations, kind of segueing into how do we actually solve these. So I've shown you solutions. I haven't told you how I'm getting the solutions. I haven't told you how I'm numerically solving these nonlinear ordinary differential equations. So we're working our way up to that. So for today, the rest of today, I want to talk about a framework. I call it the numerical solution procedure, a framework for thinking about the process by which we go from the real physical problem to an approximate numerical solution and the steps that go in between. And then talk about, if we have time, talk about how we can approach getting these numerical solutions, the various ways of getting them. We may or may not have time for that. All right, so here's the numerical solution procedure. You can keep this in your mind, and I hope that you do. I find it extremely helpful. So no matter what the field is, solid mechanics, fluid mechanics, heat transfer, dynamics, doesn't matter what the field is. It could be in another area of engineering or science or physics, whatever. If you think about this framework, this is the procedure by which we as engineers and scientists take real physical problems and turn them into governing equations and ultimately approximate numerical solutions. So let me walk through that quickly. So we start out with our physical system. So that's reality, right? So that's the observation that we see out in nature. That is the behavior of the system that we built in our basement. That is the, I was gonna say, oh, and I shouldn't say this, sorry, because 2 people were killed. Did you see this Tesla crash the other day? A Tesla crashed into a tree. Look it up online. It's completely unrecognizable. It reminds me of the pictures they used to show us. I'm sure they don't do this to you today, but in my generation, when we took driver's ed, they would show us pictures of the charred remains of people and vehicles to scare us, to try to literally scare us into good driving habits. Like I said, I'm sure they would never do that to you today. And so this reminded me of that. This Tesla, it burned for like 2 hours. They dumped 30,000 gallons of water on it. They could not put out the fire because the batteries, it was just a chain reaction in the batteries. And so they basically just had to let it burn out. And when you look at what's left, it's just unbelievable. So as it turns out, there were two people, I almost said 2 passengers, which is correct. There were 2 people in the car at the time of the crash, neither of which was in the driver's seat. So apparently they thought it was a good idea to put it on autopilot and woohoo, let's go for a joyride. And of course, the car crashed into a tree, burned up. They were fried to smithereens, and it's very sad. But this is the problem. So Tesla is doing beta testing on the general public. They are testing their autopilot software, their autonomous driving software on you and me. This is irresponsible. And, oh, by the way, what do they call it? Autopilot. What is autopilot? And what does that seem to connote? What does that seem to suggest? Oh, it'll handle everything for me. Now, if you read the manual, which no one ever does, they don't even give you a manual. It's just on that giant screen in the center of the console. If you read the manual, it'd say, oh, you're supposed to remain attentive at all times, that you are responsible as the driver, blah, 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 to take over when the car can't handle whatever situation it finds itself in. But then they go and call it autopilot, which seems to suggest something very different. It'll be very interesting to see if there's any backlash on this one, because it's completely irresponsible on the driver's part, because they weren't even driving. They weren't in the driver's seat. But it is also, I think, an outgrowth of the misinformation that Tesla is putting out there. The other problem is, and this is kind of cool on one hand, so you get these, what they call over-the-air updates. So you can one night, they're downloading new software onto your Tesla. You wake up in the morning, you drive to work, and all of a sudden it has some new feature, which is kind of cool, but also a little scary. I'm driving down the Eisenhower Expressway at 55 miles per hour, of course, always at the speed limit. I'm driving down the Eisenhower Expressway at the speed limit, and all of a sudden my car does something different than it did yesterday, because they changed the software. Did I read the revised manual that morning before I left work? No. So it's a very interesting approach to developing autonomous driving technology, one that is literally killing people along the way. All right, get off your soapbox, Cass. We'll get back to the numerical solution procedure. So the physical real system. So we want to model it. We want to understand it. Think of either of the three examples that we just went through. The first step, so there's 3 steps, 1, 2, 3. So the first step is to apply the physical laws and whatever models and approximations that are appropriate for that system. So physical laws are things like, physical laws are things like conservation of mass, momentum, and energy. So these are things that we know are true. Conservation of energy, first law of thermodynamics. We've tested everywhere in the universe, every last corner of the universe, and in every corner of the universe, I'm being facetious, obviously, we have confirmed that energy is conserved. Okay, so that's a physical law that the system has to obey. Conservation of mass and momentum, same idea. Models are approximations. So these are assumptions and approximations. So this is like the block sliding down the incline, and you say, well, let's neglect friction. Obviously, that's an approximation. So that is a model. When you do that, when you apply the appropriate physical laws and whatever models you're going to include to your system in step 1, that produces a system often, or a single governing equation. It might be an ordinary differential equation, might be a partial differential equation, might be a system of ODEs or PDEs. That is the mathematical model. So for many of your other classes, that's what you're doing. So in MMAE 202, strength of materials, 305, in 313, fluid mechanics, 305 is dynamics, 323 is heat transfer, and so forth. In all of those classes, that's what you're doing. You start with the physical system, you apply the physical laws that govern in that system, and you include whatever approximations, models, and assumptions that are appropriate, or you think are appropriate for that system, and you end up with your mathematical model, the governing equations. So if you think back and you think even of your other classes this semester, that's what you're doing. Then when you can, you get an analytical solution, you get a closed form analytical solution. So I gave the example in 313 You spend a week or so deriving these Navier-Stokes equations, and then the professor comes in one day and says, okay, now we're going to solve them. And all of a sudden they start lopping off terms left and right. Those are based on assumptions. And they lop off the terms left and right, and they get an equation that they can then solve analytically to get the solution. So that's what you're doing in all of your other classes. Now, of course, the realization is, in many cases, and that's why it's grayed out here, in many cases, that's not possible. It's not possible to get an analytical solution, and/or it's ill-advised. The amount of assumptions that have to be made in order for you to get an analytical solution are so egregious, so horrible, that the solution you get is completely meaningless for this particular system, this particular physical system. So under those circumstances, which frankly are most situations, we then have to proceed with what we're going to focus on in this class. And that is, that is the rest of the numerical solution procedure. So if we can't get an analytical solution, we have to solve it numerically. So step 2 is to discretize those mathematical equations, the mathematical model, the governing equations. And by doing so, we're going to get a system of algebraic equations. Now that should warm our heart, because now we can solve them using methods from chapter 2. So the third step, which is solving your big matrix problem, your big system of algebraic equations, that we already know how to do. That's chapter 2. So that's LU decomposition, Gauss-Seidel iteration, whatever. The piece that's missing, the thing that we don't yet know how to do, is the discretization. So that's this chapter. Which chapter is this? I think it's 8. Is that right? 8? Yeah. So that's this chapter, chapter 8. So this is the piece that's missing. So once we know how to do the discretization, we get our system of linear algebraic equations, we solve it using methods that we already have in our toolbox to get the numerical solution. Fine. So this is the focus of our endeavors for the rest of the semester. How do we do that discretization? How do we turn our continuous governing partial differential, ordinary differential equations into systems of linear algebraic equations? Let's take a simple example just to illustrate these 3 steps. So our physical system is going to be a forced spring mass system. So I have a spring, linear spring, a spring constant K. I have a mass M. I'm going to have forcing on that F cosine omega t, gravity down, and then we want to calculate U, which is the position of the mass, as a function of time. So that position, U, is a function of time. That's our dependent variable, U. It's a function of the independent variable, time. And we're just going to walk through those 3 steps. So get the mathematical model by applying the appropriate laws of physics that apply to this, and then discretize it, and then get the solution. So we'll walk through all 3 steps for this simple case, just to see how this plays out. All right, so the first thing is, first we apply the physical laws. So again, conservation of mass, momentum, and energy. And you think, okay, so what applies to this? Well, it's a wibbly wobbly spring mass system. There's no temperature change, so there's no conservation of energy aspects to this. So all we need is Newton's second law, which is conservation of momentum. Fine. Conservation of momentum. That is the governing physical principle that has to be adhered to, has to be satisfied by this system. Now we're also going to have some additional assumptions and approximations. So let's just think through the system and make engineering judgments as to what assumptions or approximations are appropriate for this problem. The first thing we're going to do is neglect the mass of the spring. Now, what's the basis for that? Well, I went to Home Depot and I bought the spring and I bought the mass. If the mass of the mass is very large compared to the mass of the spring, then that's a good assumption. If the mass of the mass is small or comparable to the mass of the spring, then that's a terrible assumption. But I went to Home Depot, I bought a large mass and a very low mass spring, so that's an okay assumption. Now, it's not correct. The spring does have mass, but it's an okay approximation. The second approximation we're going to make is that the spring acts in a linear elastic fashion. So what does that mean? That means that it behaves according to the usual elongation force curve, which is just a straight line. So do all materials behave that way? No. Do all springs behave that way? No. But I went to Home Depot and I went to the spring aisle and I went to the section of that spring aisle which has linear springs. And I avoided the nonlinear spring aisle. And I'm not going to put huge forces on it so that it ends up being nonlinear. So I'm going to stop the force, the elongation, so that it stays in this linear regime. All right, again, that is an approximation. Is any spring truly linear? Linearly elastic? The answer is no. Are a lot of springs pretty darn close to that? Yeah. And this one was from that part of the aisle. I'm also going to include drag. So drag on the mass is bouncing up and down. So I'm going to include drag. Why not? But in order to do that, I need to have a model for how that drag takes effect. So we're going to use the Stokes drag model, which applies for low speed movement of a body through a fluid. Is that appropriate? Well, oh, I thought Siri was going crazy again. I'm checking all my devices. I'm like, no, Siri's asleep still. She's fine. Oh my goodness. It's always weird hearing yourself. Anyway, okay. So hearing yourself is what I was going to say. So Stokes drag is an approximation for low speed flows. And it says that the drag force is proportional to the speed. It's an approximation. It's an okay approximation at low speeds. That's what we're going to use. It's not a physical law. It's not decreed by God. It is an assumption, an approximation that we are going to make. All right, so those are the physical laws. We've recognized what they are. We've recognized the assumptions and approximations we're going to make. And now we derive the governing equations. We apply those laws and models to the governing equations to give us our mathematical model for the system. So it is a linear spring such that we have this FU behavior. F and U behave linearly in this way. You increase the force, it just increases the U by a proportional amount. So Fs, the force in the spring, is minus Ku. So it's directly proportional to K. Negative because of the directionality of it. Then the drag. So once again, we're going to account for the drag, assuming that the mass moves slowly through the fluid as it bounces up and down. And it says that the drag force is minus the coefficient of drag C times the velocity V. Minus because drag is always in the opposite direction of the motion. If it's moving up, the drag is down. If it's moving down, the drag is up. Drag is always in the opposite direction of the motion of the body. So FD, the force of drag, is minus CV. Then we apply Newton's second law. Newton's second law. Now, have we had this discussion before? Is Newton's second law really a law? Have we had this discussion before? I think we did, but I see enough no's. So I'll just remind you briefly of that discussion. It is not a law in the sense that Newton's second law does not capture all physical behavior in the universe. It assumes that the speeds are order 1, relatively modest. It assumes that the sizes are order 1, not itty bitty small like atoms or massive like galaxies and black holes and things. So it does not account for relativistic effects. It is an extremely good model for what we call terrestrial applications, applications on the Earth. If I drop my phone and I want to know whether it's going to break or not, I will trust what Newton's second law tells me. So strictly speaking, it's only a model, but it's a really, 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 really good model such that we call it a law. So this is like the ideal gas law. I think we did have that discussion, right? So we call it a law. Does every gas behave according to the ideal gas law? No, it's really a model. And we talked about, we actually illustrated how it breaks down. But we call it a law because under normal non-relativistic conditions, it is an extremely, extremely good model, and therefore we call it a law. This is kind of annoying. Why can't we all just agree on our terms? The point being, it enforces conservation of momentum. So it's F equals ma. So I'm going to flip it around. Mass times acceleration is equal to the sum of the forces. I have three forces: the spring force, the drag force, and the weight. The mass times acceleration due to gravity, g. So I'm going to have three contributions to the force. And actually four, sorry, I forgot the forcing. We're forcing it up and down, the F times cosine omega t. So there's actually four contributions to the force, and that's equal to the mass times the acceleration. Now, acceleration, you'll remember, that's the derivative of the velocity with respect to time, which is the second derivative of position with respect to time. So ma, we could write as m times du dt, velocity, or, sorry, dv dt, derivative of velocity, or d squared u dt squared, so second derivative of position, which is what we'll do. And then the four forces: force of drag, minus CV, force of the spring, minus KU, the force of the weight, M times G, so minus MG, and minus the force of the forcing force. Oh my goodness, that's minus F cosine omega t. See the helicopter on Mars? I think it's so funny because I understand why it's exciting, but I also understand why the general public looks at this as kind of like, what are you nerds getting so excited about? It literally lifted off the ground, went up 10 feet, it rotated in place, and then landed. And then everyone cheered. Woohoo! It's cool because obviously Mars is very different than the Earth. We have a helicopter that we successfully, safely got to Mars. It survived the environment there, and it actually worked in the very undense, the very what's the word I'm looking for? The very lacking in density atmosphere of Mars. So that's kind of cool. But I can understand why the general public be like, tell me when we got Martians and cool science fiction-y kinds of stuff going on. Anyway, okay. So I have my sum of the forces. We're almost out of time, Castle. Let's get going. And then I put in for the acceleration d squared u dt squared. So if I divide through by m, this is an m times that. So if I divide through by m, you get an m here, the m cancels with the mg, and an m here. So this is the result of step one, and we'll stop there. So that is the result of step one. That is the governing equation that accounts for the physical laws and the assumptions, approximations that we made. We applied them to our real actual system, and 8.2 is our differential equation. In this case, an ordinary differential equation that governs the motion of the system. All right, so we'll stop there. We'll pick this up on Thursday. In the meantime, I don't know, do something constructive. Wow, that was profound. Thanks, Castle. We couldn't have done it without you. All right, see you then.